Hello everyone, welcome to the course Mathematical Aspects of Biomedical Electronic Systems Design. This is a TA session and the topic that we are going to focus today is percolation theory and its application in biological tissues. Before we begin with this topic, this is in continuation with the application and how disorder exists in biological tissues, which we had covered in the previous TA session. So before we plunge into this particular aspect of charge transport in biological tissues, let us first have a quick recap of the disorder present in the biological tissues, and then we will move on to this new topic. For any kind of queries, please feel free to put your questions or queries in the comment section. So, what is the meaning of disorder? We had talked about disordered systems. We first reasoned that what exactly means disorder. The most simple answer could be anything not in order. And then we tried to motivate ourselves that why study disorder in biological system? What is the reason? What is the importance of studying disorder in biological system? We study physics to understand our daily routine that we do, cycling, walking, everything is related to physics. So in a similar way, why do we want to study? So as biomedical engineers or someone who is interested in the field of bioengineering, why disorder is important? Why studying disorder is important? So one of the most common reason that we gave is that cancer, a very widespread disease, and it is certainly a cause of large number of deaths in the world, is a cellular level disorder. We will talk about it in some later TA sessions. But this itself is big motivation to understand what exactly is disorder and why to study disorder. Studying disorder in biology was a little big step. So we went step by step by taking examples of existing systems which have been completely established as far as their disorder is concerned. So we began with first example, which was disordered semiconductors. Disordered semiconductors have been used in applications such as flexible OLEDs, flexible displays, which you may have seen in the recent media. And what is the difference? Then we talked about what is the difference between disordered semiconductors. We took example of amorphous silicon, and we tried to reason that how amorphous silicon, which is mentioned here, is different than single crystal or periodic silicon. We reasoned that there are three different kinds of structurally different kinds of silicon available. First is single crystal, which is locally as well as globally ordered. Whereas in the case of polycrystalline, there are local patches which are ordered, but overall if we see the crystal, if we take a wafer of polysilicon, then and if we do studies like X-ray diffraction, we will find that the structure is not continuously ordered, but there are some patches which presents ordered structure, and then there are some patches which does not present ordered structure. Overall it is not an ordered structure, but locally it is ordered. Whereas in the case of amorphous, which is completely disordered system, even local ordering is absent. Then we tried to understand that what kind of disordered semiconductors are available. Inorganic, like amorphous silicon and polysilicon, and then organic conducting polymers such as P.PSS. So when I was referring to flexible OLEDs, flexible displays, or even flexible devices, if you happen to design some biomedical devices, it is good to have flexibility because our skin is not planar, and whatever sensor we fabricate, it has to be conformal. So another reason why we included disordered semiconductors in this particular session. And then we presented a comparative analysis of how these three different kinds of structurally different kinds of silicon fare in terms of their subsystems, which is short range order, which is present in all of them. Defect subsystem, it is present in again all of them. Morphologically, single crystal silicon stands out compared to polycrystalline and amorphous silicon. And then medium range order, medium range order as we discussed, which is even not even locally disordered, is present only in amorphous silicon. Now these kind of systems also translate into different kinds of band structure arrangement. This is what we studied last time. We studied that how in case of single crystal silicon, the band diagrams, which is valence band and conduction band, are clearly separated, and in between there is something called as forbidden gap. There are no energy levels which are allowed, there are no states which are available for any charge carrier to occupy this particular location. Whereas in the case of disordered semiconductor, we took an example of amorphous silicon, and what we found that there are localized states which extend into the forbidden gap when compared to the single crystal silicon. And what are these localized states? These localized states are non-continuous patches with allowed levels of energy within the forbidden zone. You can imagine it in this way. Then we saw that if it is E versus X, within that you can have multiple energy levels within the forbidden zone, and these are all allowed state and they are not connected, and that's why they are called localized states. Again, we are just scraping through the surface. There is lot more that goes into understanding these localized states. The foundations lie in the field of quantum mechanics, but just to appreciate the structural difference between single crystal silicon and the amorphous silicon and how it affects the band structure arrangement, which will eventually affect the transport properties, we are trying to understand at first order. Then we try to understand what are these localized states in terms of a clear band diagram which we can assume for disordered semiconductor, which is amorphous silicon. That is a case example here. So what we found? We found that like we have bands, valence bands and conduction band in case of single crystal silicon, in case of amorphous silicon, we have something called as mobility edge. The mobility edge is something where after, if the electron is transported here, then the conduction will be seamless. But somewhere here, where the states are localized, the conduction will be unlike the way when it is after the mobility edge, which means here the conduction will be, the way electrons transport will be different the way they transport when they cross this mobility edge. Then we also looked at another example of polymer composite. We had discussed that polymer composite resemble to some extent the structure of tissues and can be modeled and therefore are useful in understanding the structure of biological tissues by the means that they capture the complexity and the associated randomness. We took 3 examples here. The first example was, there is this polymer composite which contains polymer and nanofibers as filler material. So these nanofibers, as you see, are filler materials which are electrically conducting, which are carbon nanotubes here. And in the second structure, we introduced small silica nanoparticles which are insulating. And in the third figure, we found that they have introduced larger silica particles. And why did we discuss all these things? We were discussing that how structure can affect the physical property. What is the structure property correlationship as far as polymer composite is concerned? Similar things, similar concepts can also be applied to biological tissues, and how the structure property correlationship exists, this is something we are going to see today. We then also tried to understand that if given a polymer composite which has conducting islands in patches which are connected, loosely connected When I say loosely connected, it means there is no continuous path between these two. This part doesn't exist, but there are some fine conducting islands which are present in between these two conducting islands, through which the conduction happens, and how that conduction happens is something we are going to understand today. Then we tried to then in the previous session we tried to understand that how the equations of conduction work as far as such a disordered conducting polymer system is concerned. We talked about an exponent which is dependent on temperature, and then we found how this particular conductivity, which is again temperature dependent, can be expressed in terms of exponential of this particular function, whereas this energy which is required for the charge carriers to transport from one conducting island to another conducting island is again dependent on temperature and is also a function of this exponent. Please keep this picture in mind, because in next few minutes we are going to delve in more detail keeping in mind this particular picture. Then we moved on to an example of explaining disorder in biological system. We took example of cell migration. Why cell migration? We tried to reason that cell migration is a very common phenomenon which is observed in processes like wound healing, tumorigenesis, and embryogenesis. So these are the three main processes where cell migration is commonly observed, and then we saw this clip wherein we could see that there is structural variation that is happening across the cells, and we found that there is no specific order or there is no specific direction in which these cells are moving or these cells are changing the shape in order to migrate from point A to point B. Then in the next part we try to understand that what really governs this particular cell migration and how can we characterize the structure of cells and the associated disorder. For that we also looked into a vector plot which gave us further detail about the extent of disorder in the cell migration, where we could see that the vector fields associated with the migration or the movement of cells in different direction gave us a very clear idea that there is no specific direction in which the cells are migrating, rather it is very disoriented. And how we can understand the structural property? We can understand the structural property by using this equation, structure factor. Structure factor is generally used for understanding crystal structure by the means of techniques like X-ray diffraction and neutron scattering. Though in this particular study it was done by image analysis, it can also be done by image analysis. And what we try to reason is how these cells, when they migrate, have both spatial as well as temporal variation. Now what is something that can correlate both spatial and temporal variation? This is Fourier transform. So we did a Fourier analysis. We tried to understand that how it can be explained by combining these two aspects, and that's why this particular structure factor contains both spatial and temporal terms. And these two parts of this equation, the first part contains Rayleigh scattering term which is associated with random and uncorrelated scattering, and then this second part is associated with Brillouin scattering term which is periodic and correlated scattering. We don't have to go into the details, this is just to give you a glimpse that how one can understand or appreciate the extent of disorder in different kinds of system. And this is where we ended. So let us now understand what exactly percolation means, what is percolation theory, and finally we will try to look for some examples in both existing and established system as well as biological systems. So let us begin with understanding percolation theory. So one very interesting way of understanding percolation theory is to do a wire mesh experiment. So what you do, you take different strands of wires and then you solder them or you connect them by some other means, and then you have a common end at each side, and then you apply potential. Now what you do, you measure what is the voltage drop and hence eventually the resistance. So you can measure the resistance of this wire mesh. So let us call these junctions as nodes. So I will name them as node 1, node 2, node 3, node 4, and let's say there are n junctions, so this will be node n, and it's a matrix, so there will be a component ij, so it can be termed as node 1 1, node 1 2, node 1 3, node 1 4, and node n I n ij, where I corresponds to the row and j corresponds to the column. Now you have measured the resistance for this entire mesh circuit. Now what you do, you remove selectively any node that you feel like. It's a random phenomenon, because if you let's say have 137 by 137 matrix, which was the case in this particular example when the authors did the experiment, it's difficult to select that why particular node will be removed. So you associate some randomness to it, which we will discuss now, and then you remove a particular node. So let's say I removed node 1 2, then I removed node 1 4. After removing node 1 2, I will measure the resistance. So there will be a resistance after node 1 2 is removed, and then there will be a resistance after node 1 2 and 1 4 is removed, and then you plot resistance versus such node removal instances, and what you will get is a graph looking something like this. So this is normalized conductance. So when I say normalized conductance, it is the conductance at that instance of time divided by the conductance at t equal to 0. T equal to 0 means the instance where this experiment was started, and t equal to t is the time when we are looking at the conductance at each instance of the x axis. This is x, this is y. So what do we see here? We see that as we remove the number of nodes, so this resembles how many such fractions of nodes of the total nodes. So let's say if there are 200 nodes, so 0.1 would mean 10% of these many nodes, 10% of 200 nodes are removed at this particular point, and then they are measuring the resistance. So something here at 10%. Then if I look out for 20%, it will be somewhere here, and then 30%, it will be somewhere here, %20 is here, 20% is there, and finally when I go to around 40%, this is the most interesting aspect. Finally when I go to almost 50% reduction in the overall number of nodes, the normalized conductivity almost drops to 0. So there are two observations here. One, there is a linear decrease in resistance, and second more important observation is after let's say xc, or the fraction of nodes which are removed greater than 0.4, my sigma by sigma naught is tending to 0. Let us discuss these observations in sequence. So if it is linear reduction, how is it possible? So let us look at this particular diagram. What are we doing? We are breaking some electrical junctions which are contributing flow of current from this point to this point. And this is just to show the flow of current. It doesn't necessarily go like this. It will definitely go through this and the shortest resistance path, which all of you would know. But just to illustrate the point, so as soon as I start removing each node from here, the number of junctions which are contributing to the conduction are reducing, which means they are increasing the overall resistance of the circuit. Why? Because the overall path length which now the current has to take is increasing. For example, if the current was flowing like this and if I broke this node in between, it's possible, right? As I discussed, it's a random experiment. I'm removing any node at random. If I have removed this, then the current has to go from here to here. And then if I have removed this junction here, then it will have to find another route which is from here to here. So what is the overall length if you check here, and the overall length if you compare, let's say the length at this particular point was L1 and at this particular point is L2, considering the radius does not change, then by R equal to rho L by A, if length is increasing, the overall resistance will also increase. So now okay, we have understood the linear increase in the resistance as a function of removal of nodes or conducting nodes in this particular section. Now what happens when a particular fraction percentage is reached? I am referring to the point number 2, wherein after Xc crosses 0.4, the normalized conductivity comes back to 0 or approaches 0. They have not zoomed in this particular graph, otherwise you would see that how it is approaching 0, very small values of conductivity. Now why is that happening? So let us understand this fact, and this forms the basis of percolation theory. So I am removing node after node from here, from here, from here, from here, from here, from here. Now if I keep doing and repeating this process, I will be left at a particular point where there is no single line which can continuously connect. If I call this point A and this point B, there won't be any single line which can continuously form a network of such nodes from point A to point B. And at this point, and remember at this particular point the conductivity drops to 0, and this particular point where conductivity drops to 0 is something called as percolation threshold. So what we are trying to say, that if there are nodes in a network and the conduction is happening through the connected nodes, and if we keep tripping the nodes one after the other, we will reach a point, and that point, which is termed as percolation threshold, after which there won't be any path, there won't be any continuous path which can provide conduction from point A to point B for the current to pass through. So let us understand this briefly. I am not going into the detail in terms of probability. Why probability? Because it is more of a random experiment. You cannot say that in a structure, in a real world, in a practical world, you cannot really say that when you are making such structure which has nodes, interconnected nodes which contribute to the conduction, will snap off or will not be connected at this particular point, and that's why you need to associate that probability to each of such nodes. So how we can do that? So let us assume that there are n number of nodes. So we will see that there are n number of nodes. The same diagram I am drawing just for the sake of repetition and familiarity. And let's say that there is a probability P probability P, which is associated with how much is the probability, this is the probability of occupying one node, occupying such nodes. So if there are n such nodes and the probability for one is this, for one such node is this, then the overall probability for n such nodes which are occupied would be P into n. On the other side, there will be nodes which are not connected, which are not occupied. So what will be the probability for that? It will be 1 minus P into n. So now we are with two probabilities, 1 minus P into n and P into n. And let us understand this particular probability in terms of the percolation threshold. Now when this n reaches the value of percolation threshold denoted by Pc here, the conduction from point A to point B happens. So this is an example of a maze which is generally used in different papers or research articles to emphasize the percolative aspect of any kind of system. Similar is the case used here, that when the percolation, the fraction or the number of nodes, if we continue with the same terminology, the number of nodes, if they are less than the percolation threshold number, then there won't be a completely connected path. Whereas if the number of nodes, interconnected nodes, are larger than the percolation threshold, then the percolation or transport would happen from point A to point B. So this is what we were discussing, that each site is associated with a probability P. Let n sites such in a square lattice. So one more point that I want to emphasize here is, we are all discussing the first order problem, and that's why we are taking the simplest case, which is square lattice. In real life there may be honeycomb lattice, which will look something like this, and these lattices will be interconnected. So these hexagons when interconnected will form honeycomb lattice, and then there will be triangular lattices also, where we will form structures where the unit cell of that particular structure will be a triangle. For that, these values would definitely change and have to be calculated, but just to begin with, we are going for square lattice. For more references into triangular and hexagonal lattice, you can please refer to this book. It has quite rigorously explained all these processes and how you can associate probabilities for each such type of lattice, whether it is square, honeycomb or triangular. Now when we talk in terms of biological tissues, or before that, let us talk about the polymer composites that we had discussed. We talked about conductive, we talked about a cuboid which was the polymer, and then there were carbon nanotubes filled in this. In this particular case, this was the filler material, the carbon nanotube, the conducting filler material. This was the conducting part. Now why I am discussing this? I am trying to draw parallel between the percolation that we just studied and this polymer composites. How we can draw parallels? We can consider that in a matrix, in a polymer matrix which is insulating, we have induced some carbonaceous elements, in this case carbon nanotubes, which are electrically conducting. And till a particular fraction is reached, which is Pc. So let us say I am taking 1 gram of polymer and I am putting 0.01 gram of CNT, and if this particular volume fraction corresponds to something which is less than Pc, Then in this particular polymer composite, if I apply current, there won't be a continuous path. I won't be reading any potential at a voltmeter if I put here. So just to make it more clear, if this is a polymer composite and I am applying a potential here, and I am reading what is the current here. If I go for this particular part where P is less than Pc, which means the number of carbon nanotubes which are mixed in this particular composite are less than Pc, then I won't be able to form any single conductive path which can complete this circuit. Whereas if I increase, let's say this is just an example, these are not some real values, let's say I increase to 0.04 for example, so I increase it by 4 times, and for 4 times, let's suppose we know that for 4 times this particular value will cross Pc, so we have a condition of P greater than Pc. In this particular case, what we will find, there is a continuous path and the charged particles are able to cross from point A here to point B. Why? Because now there is a continuous percolative path between point A to point B. So this is a kind of formal definition which has been described in this particular book. Each side of a very large lattice, in terms of lattice, it means it is a kind of solid. Even this can be considered as a description of lattice, is occupied randomly with probability P independent of its neighbors. Percolation theory deals with the clusters thus formed, in other words with the group of neighboring occupied size. So here, if you would have paid attention to the previous slide, you would have appreciated that how adjacent nodes are very important, because if I have short this particular adjacent node, then there won't be any continuity between this node and this node. So this adjacent, which is also called as nearest neighbor node, so this node, which is also called as nearest neighbor node, is very important in percolative transport. So this particular node means you share an edge. If you are sharing a node with this particular cell, it doesn't mean that it is nearest neighbor. I will draw that again here. So these two can be considered as adjacent nodes, whereas the adjacent or nearest neighboring nodes, whereas these two are not sharing an edge, they are just sharing a node, and that's why these two, if I were to name it S1, S2 and S3, S1 and S2 are nearest neighbors, whereas S1 and S3 are not nearest neighbors. So this is what was about percolative transport. Now we will try to understand, we have seen how percolation happens, but at the level of conducting islands, which in this particular case was carbon nanotube to carbon nanotube, how transport happens, that we will now try to understand. So the process by which such kind of percolative transport occurs is called hopping. Hopping, by literary sense, it means jumping from one point to another point. So let's say there is a point A and there is a point B. You hop means you jump from point A to point B. In the literal sense, it means that. And even if we consider in terms of charged particles, let's say we consider electron, the same can be associated with holes. The holes jump from one point A in space. So this is space, this is x. So electrons will jump from one point A to point B. So what are the things which are and this is how the percolative transport is formed. So what are the things required for the electron to achieve this jump successfully? One, as we would be able to appreciate is the distance. So let's say this distance is xab, which is called the hopping length. And second, how much energy has been given to this electron to jump from point A to point B. So this energy is mostly either thermal or it is electrical. By electrical I mean it's electric field. And now if you are able to recall the equation wherein there was a temperature component for the polymer composite, we had written that it is exponentially dependent on W of gamma over kBT to the power gamma, and there was a temperature dependence. And this temperature dependence stems from the fact that for an electron to hop from point A to point B, one of the factors which is required is energy, and that one of the energy forms which can do or which can help electron achieve that hop is thermal energy, and that's why there is a temperature dependence. So what do we conclude from this particular point? We conclude that temperature dependent transport, when I say transport I am talking about electrical transport unless specified. Temperature dependent transport is a signature of disordered system, is a disordered system. Why? Because if you are supplying some extra thermal energy to the system, you will find that the conductivity will increase. Now what? So this is one way. This is the second way. Now let us go to first way. What does it mean by hopping length? Now going back to the previous slide where we had brought in that picture of polymer composite where there was a polymer matrix and then there were carbon nanotubes filled, and there were two cases that we discussed. One was P less than Pc and second was P greater than Pc. Now let us try to understand these two cases in terms of hopping length. Let's say in case of P less than Pc, I will just try to draw how it will look from a top view. So I am drawing a top view here. So this is the case for P less than Pc. So I will put it inside a square box so that it doesn't confuse. So these are all carbon nanotubes, and this is the case for P less than Pc, which means the conduction is not happening. One of the reasons why conduction would not happen, and the fact that we said that it is less than volume fraction, what does it mean? The length. So this is a carbon nanotube, this is electrically conducting, this is another carbon nanotube which is electrically conducting. To make a jump from one conducting island to another conducting island, electron not only needs energy, which we discussed, it also needs a particular length which can make that jump feasible. This length or the hopping length that we discussed cannot just be any value, and that is dependent on different factors such as what is the temperature, how is the fraction of carbon nanotubes arranged in a particular system, and within the carbon nanotubes how fast is the conduction possible. Considering all these facts, there is a limitation to which electrons can make a jump from conducting island 1 to conducting island 2, and this limitation can directly be correlated with the volume fraction concept that we studied in previous slide, which says that if a particular volume fraction is not reached, if the number of conducting islands are not at a particular weight percentage in a matrix, then this conduction will not happen. Now similarly, let us try to take the case where this volume fraction is enough to form a percolative path. So I am just drawing a denser carbon nanotube system in the same polymer composite, and what here happens is, if previously the mean length for the electron to hop was L1 and here the mean length is L2, here L2 will be less than L1 and L2 should be less than or equal to the hopping length, which is the length required for the electron to make that hop, to make that jump from point 1 to point 2. So we saw how these concepts of polymer composites, their structure, their electrical transport, and how the transport happens, how percolation theory comes into the play, and how that percolation theory is connected to the fundamentals of charge transport in such systems which is percolative. All this overall picture is now clear to you. This is what we hope. Now just to give you a little more glimpse, we won't go into the detail, we will talk about two different types of hoppings which can happen in a system. This will again make use of the previous slides discussion that we had, where I had asked you to pay some more attention on the concept of nearest neighbor. So the first hopping itself, first type of hopping is called nearest neighbor hopping. So the name itself suggests, again we go back to that picture, our same old picture. This is a conducting part, this is another conducting part, and this is the nearest neighbor. So if this is the point where electron is located, the electron will make a jump from point A to point B. This is an ideal system, doesn't exist. So if we look in terms of polymer system, this is a carbon nanotube and electron is making a jump from point A to point B. This is the nearest neighbor, this is A, this is B. The highlight of nearest neighbor, if I were to draw it in terms of energy, so let us say this is E1 and this is E2. This is E1 and E2. The electron, let us say, is here, and this separation, let us say, is E delta. So when you increase the temperature sufficiently, if you remember that sigma E equation that we had discussed for disordered composite, this E corresponds to the energy which is required for that electron to make this jump. So if you supply enough temperature here, which is thermal energy, it can make this jump from here to here. Such a jump would be called nearest neighbor hopping. Now let us look at the second type of hopping. In this type of hopping is generally observed when the temperatures are not elevated. You don't have that high amount of thermal energy to provide enough input to the electron to make that jump. So if we draw the same diagram, if this was the energy E2 and this was energy E1, then the jump made from here to here is nearest neighbor, and let us say there is an intermediate energy level, let us say this is E3, which is available because it is a disordered systems. In a single space, energy domains can lie even within the forbidden zone. So let us say I have energy level E3 and my electron is still here. This jump is not possible because I don't have this temperature with me. In that case, what would happen is, this is a probabilistic event, which means there is a probability associated with this particular electron making a jump from here to here. Now why this jump looks more feasible there is one important reason here which can easily be seen just by the look of it, that the overall energy required for the electron to make this jump, let's say this is E delta 2 and this energy is E delta 1. So E delta 1 is greater than E delta 2. So even if they are spatially located at different instances, electron, because of its low energy state for this particular level, it can jump. I am saying it can jump because again there is a probability associated with that. It can jump from this state to this state. Such a jump when made is called variable range hopping. Or VRH. And these two hopping types are the hallmark of any kind of disordered semiconductor or a polymer composite or any kind of disordered system when you consider its transport behavior. So whenever one has to study a disordered system and one has to characterize the physical properties such as IV or thermoelectric behavior, because as we discussed, such disordered systems are very temperature sensitive. For these two and many other types of studies, variable range hopping and nearest neighbor hopping is something that one should look for. So having understood and studied some aspects of percolation theory and how the charge transfers from point A to point B, what are the different hopping mechanisms using which the charge can hop from point A to point B, let us now look at some examples which have been cited in the literature. So this is one example, and I chose this example because it resonates with the previous discussion on polymer composites. Why I keep choosing polymer composites will be clear very soon to you in the next slide. So in this polymer composite, this is a conducting part. It is a carbon nanofiber. I am not going through the detail of carbon nanofiber. The difference between carbon nanotubes and carbon nanofiber is that carbon nanotubes are hollow. Carbon nanofiber is a proper fiber which is solid all throughout. So this is a carbon nanotube and this is a carbon nanofiber. So what they did, they took a polymer and then they kept filling this carbon nanofiber, and then they measured the resistivity of the composite at different filling fractions. This filling fraction is the same volume fraction or packing fraction. There are different names to it, so please don't get confused. So they kept filling at different concentrations. So this is plotted for at x-axis and the resistivity is plotted on y-axis. So when they kept filling and increasing the concentration of this carbon nanofiber in this polymer composite, what they found was the resistivity, which was at around 10 to the power 16 ohm centimeter at P equal to 0%, there was no carbon fiber. It reached to 10 to the power 2 ohm per centimeter when P was increased to 12%, which is volume by volume. If you see this value 10 to the power 16 to 10 to the power 2 ohm centimeter, there is a staggering change of 10 to the power 14 times between the conductivity values. So just by increase of conductive fraction in the polymer composites, you can achieve very high resistivity. We can convert a material with very high resistivity to a material with very high conductivity. Now such systems, because they are primarily composed of polymer, can be used for many applications such as flexible devices, stretchable devices, and as we had discussed, Such flexible and stretchable devices are very useful in designing biomedical sensors. So now all this thing, if you see in a single picture, percolation, begin with disorder, then percolation, then we are talking about hopping. If you see this in a single picture, we find that it's very much related to biology and biomedical systems alike. The relevance in biology you will be appreciating more when you go to the next example. So next example is chosen again from the literature, and here we have taken the example where collagen, which is the most abundant type of protein found in animals, has been modified by introducing metal elements, by decorating it or encapsulating it with metal elements, and then they have studied its electrical properties. First we will try to see what exactly has been reported, and then we will try to understand and appreciate this work, how is this important. This slide will also form the culmination of our discussion on disordered systems and percolation theory, so try to pay little more attention to this. So in this particular case they have used gold collagen nanofibers, and what they found was when they decorated this collagen, you can see this collagen nanofibers with gold nanoparticles, these are gold nanoparticles, they started conducting. This overall system became electrically conducting. And what type of electrical conduction was found here? So if you see the structure more carefully, these gold nanoparticles are the conducting domains, and this collagen is the matrix or the base. Now if you imagine such collagen bundles in the entire matrix with such gold particles, what would one try to deduce given the discussion that we have been having? The most important conclusion that we would have is there is no direct contact between these two gold nanoparticles, though they are very closely situated, mostly in terms of few nanometers. There is no direct contact. So what kind of transport would be happening? Yes, it would be percolative transport, and that's what was reported in this work, that just by decorating them with gold nanoparticles they were able to form a percolative network of conducting domains, such that in the matrix when they were studied for IV characteristic, they found a finite value of resistance within collagen fiber networks. In a similar work, they introduced iron into collagen fiber network, and then they compared the IV characteristic of collagen decorated with iron and collagen by itself without any kind of metal nanoparticles. When they compared, and they used a kind of current sensing atomic force spectroscopy, which means there is a very small tip. By very small means this tip diameter would be around hundreds of nanometer or maybe less than that. With this they apply, so this they bring to the surface very close. This separation would be around 10 nanometers or 20 nanometers, and then they apply field. Since the separation is very less, they could even sense the current which is generated after completing the circuit. And when they did this experiment, what they found was there was a 6 times enhancement after iron nanoparticles were introduced in the collagen nanofibers. This is similar to the result that we saw for polymer nanocomposite in the previous slide, where there was around 14 times change, 10 to the power 14 times change in the resistivity values when the packing fraction of conductive filler elements was increased. So this is a similar situation, just that here collagen, which is a kind of animal protein, is used. Now one would reason that what is the use of all these studies? They have done some extensive and very sophisticated experiments. What is the use of all these studies? So one of the important reasons why collagen was chosen to perform such experiment was that A, it is abundantly found animal protein, and B, it has a very long shelf life, like it can last at least for 14 years when kept in a proper medium. Now how would this help? How does this information help? Let us say you want to make an implant which requires collagen fibers to be compatible with the place where it has to be implanted, and there has to be some kind of signal that you want to see upon changing the, let us say you have a system where you want to implant a collagen based sensor, and then you want to measure if this particular system is observed some change or not. When you do that, since these are biocompatible materials and collagen will promote, it has been reported in this particular work that it will promote stem cell formation, we can see that this particular application can lead to development of many different biosensors. Similar is the case for this particular application also. So we saw, to summarize this particular lecture, we saw how disordered systems can be used in biological systems to understand their physical properties, their structural properties, to understand how the electrical transport happens in biological systems, how they can be modified to make them electrically conducting, and how this percolative transport occurs. All these things are very useful for any biomedical engineer to design such biocompatible systems with using biomaterials or biocompatible polymer composites. And once we understand the electronic transport properties, we can engineer the structure by modifying, let us say, the percentage composition of filler elements that we just saw. It can affect the conductivity. We can also change its structure. All these modifications can be performed, and different novel kind of devices can be developed. So I hope you enjoyed this lecture. If you have any kind of doubt, please feel free to put your questions in the forum. Thank you so much.